Hello everyone, and this is my reflection about photolithography. And today, and this is my reflection on the technology that shaped nearly all the electronic devices we depend on daily. And yet, it's something most of us rarely think about: photolithography. Okay, and this process, which literally means writing with light on stone, is crucial in creating microchips and that power our cell phones, computers, and countless other devices. Without photolithography, we wouldn't have the powerful processors that allow our devices to perform complex tasks in the blink of an eye. Interestingly, photolithography isn't a new concept, okay? It was invented in 1855 by Alphonse Poitevin, years before modern computers or smartphones were even imagined. This process began in a very different context, and yet today it has evolved into a highly sophisticated technique that sits at the heart of modern electronics. As I dive into the process and impact of photolithography, I offer to I hope to offer a fresh perspective on how this technology bridges the past, present, and the future. And first is the process of photolithography. To appreciate photolithography, let's take a closer look at the steps involved and imagine you are in a high-tech lab with the silicon wafer, the smooth and the shiny disk that will eventually become part of a microchip. Okay, so smooth like a silicon wafer. Yes, that smooth and shiny disk. Okay, imagine that. And the first step in photolithography is cleaning. The silicon wafer is treated. My bad. The silicon wafer is treated with chemicals like hydrogen peroxide to remove any contamination from handling and transportation. This ensures a pristine surface for the upcoming layers. And next is a masking layer is added. Think of this like the foundation of a house. It's essential to have a stable base. Yes, for every house, you need to have a stable base to build a house. So, a silicon layer is first applied, followed by a chemical called hexamethyl disilazane, or HMDS for short, which helps ensure that the photoresist, our light sensitive paint, will adhere properly. Then, the wafer goes through a process called spin coating, which spreads the photoresist in a perfect uniform layer. And this layer is so thin, typically between what's that, with zero point 0.5 and 2.5 micrometers. And that's almost invisible to the naked eye. And after this process, next one is the wafer is baked lightly to remove any excess solvents, ensuring that the photoresist layer is stable for the next stage, exposure to light. And here's where the magic of the photolithography really begins. The wafer is placed under a photomask, okay, which contains the specific pattern for that chip layer. And then it exposed it is exposed to ultraviolet or UV light, and this light chemically changes the photoresist wherever it shines, creating a patterned layer on the wafer. Okay? And now after that, the wafer goes through a developer, okay? Washing away parts of the photoresist to reveal either a positive or a negative image of the pattern from before, the pattern that the UV light created. Okay, depending on the type of photoresist used. And finally, we reach the etching stage where chemicals remove unprotected parts of the wafer, exposing the silicon underneath. At the end of this process, silicon dioxide is deposited in the wafer, and these steps are repeated multiple times to build up the different layers and intricate pathways to make up a chip. And as I reflect on this process, I am reminded of the dedication and precision required to achieve the level of miniaturization we see today. Each step represents years and years of development, and each tiny adjustment in thickness or even in wavelength brings us closer, smaller, and more powerful devices. And this entire process is a reminder of how science and creativity can combine to produce something truly remarkable. And next one is the one of my my notes on this reflection is the improvements in photolithography. And over the years, photolithography has undergone significant improvements. In the early days, mercury vapor arc lamps with wavelength of 365 nanometers were used for the light source. But as demand grew for high resolution in microchips, these lamps were replaced with more advanced fluoride-based lasers and with shorter wavelengths, allowing for finer details and better precision. Today, we're working with laser sources at the extreme ultraviolet range, down to just a few nanometers. And knowing this advancements, I can't help but to think of Moore's law. Okay, Moore's law predicts that the number of transistors in a given space doubles roughly every 2 years, with which requires these improvements in photolithography. With each advancement, chips become more capable of handling higher processing power and in the same or even smaller spaces, like I said in the previous video. This shrinking of transistor size has allowed us to reach incredible milestones. Today, today, the industry standard is down to critical dimensions of 14 nanometers, and companies are pushing even further. Without photolithography's evolution, achieving these feats would have been impossible. This progress doesn't happen overnight. Okay? So companies like ASML and Sakuso manufacture the equipment that makes modern photography possible. And my summary and final thoughts about this reflection is I see a field of where past inventions meet modern technology to create a future that this process, with its roots in the 19th century, has evolved into an essential part of our digital world. This precision and innovation require required to develop photolithography from mercury lamps to EUV lasers represents both human and ingenuity and our drive to constantly improve and refine what we create. Looking forward, photolithography will continue to evolve with even smaller critical dimensions and new light sources on the horizon. However, this advancement must come with a commitment to environmental responsibility and a willingness to collaborate across borders. As technology becomes more advanced, it's important to remember the values that will guide its development, innovation, sustainability, and cooperation. Lastly, photolithography may be hidden behind the screens we touch and the devices we use, but its impact on our life is undeniable. I hope this reflection offers a glimpse into the world of microfabrication, showing how a technology that began with writing with light on stone has transformed into a crucial part of our everyday lives and our global economy. And that's it. That's my reflection on this video. Thank you very much.